Okay, I'll start recording. Let me see if we can start. So, what I was saying yesterday is that now we're going to start talking about how to solve systems of equations, just because they kind of appear in many situations. Like one of the situations where they were showing up yesterday, if you remember, is when we were trying to find the inverse of a matrix. But systems of equations are actually, I mean, a lot more common than just for that. Uh, More or less, all the course is essentially about solving. Like 90% of the problems in this course is just like about solving systems of equations in one way or another. So it is more or less like the only um, tool that we have at our disposal in linear algebra. Almost every, yeah, there are not that many things besides doing that. Okay, so what I was saying is that for systems of equations, like the ones that we care about are the ones that are called linear. Let me see where I dropped the, here it is. We care about the ones that are called linear systems of equations. And so when the word linear just means is that every time you see the variables, they always like appear, raised to the exponent 1, and that you never have mixed things like x, y, or x squared, or even more weird things like cosine of x or sine of x. You only have like the x and y kind of like on their own without any other operations. So what that does is kind of simplifies like the equations a lot, and so that's what allows you to say a lot, many things about them because they're so simple. So one of the things that I was explaining yesterday is that for systems of equations, they're essentially for systems of linear equations, there are essentially three things that can happen. You have a unique solution, right? Which in this case, if you think of the equations as representing lines, that just means that the two lines meet at a single point. You could also have zero solutions, which in the case of lines, that means that the lines were parallel, so they never intersect. Or you can have, like in this case, something slightly more silly, which is infinite solutions, because somehow like the two lines were cyclically the same, so the lines always intersect. So this 1, 0 or infinity business kind of keeps happening, and that's what's interesting about systems of equations. So even when you have more variables around, like when you have like more variables like this, like x, y, and z, x, y, and z, like what you have, like what you get here instead of lines are called planes. And so when you have two planes, which you should think about as two pieces of paper, they either intersect in a line, which is what you see here. When they intersect in a line, that's infinite solutions because a line has infinite points, or they're parallel, so zero solutions, or you could have three planes and kind of arrange them so that all of them exactly meet at a single point. That one is harder to draw, so that's the one I showed you on GeoGebra at the end of yesterday's class. But the point is that they are always, even for the case of planes, it's 1, 0 or infinity. And if you have more variables like x, y, z, w, then like you cannot really do the pictures, but the same would happen. Like it's only one solution, zero solutions, or infinite solutions. Okay, so that's the only thing that can happen in linear algebra for these systems. So what we're going to do today is kind of think about these systems in a slightly more useful way with the help of matrices. So, so yesterday I was telling you about like the geometric interpretation of these linear systems. Now we're going to talk about like the matrix interpretation of these systems of equations. And you'll see that's like the most convenient thing to use in order to solve them, which is basically what we're going to spend doing today. So for example, okay, let's start with something easy. So imagine that I give you this system of equations. Okay, so the first thing that we can do is to think of, okay, now you see two equations, but we're going to think of those two equations as a single thing. And the way to do that is to think, for example, of the right-hand side as a vector. So we're going to think about these two equations as being the components of a vector. So like, here's like the idea. Think of the equations. So by that, I mean that instead of thinking of this system as two separate equations, you can say, well, the right-hand side is a vector -1, 9. And what's the left-hand side? It's, well, it's two vectors whose entries are x minus y and 3x plus y. Is that making sense? So it is, like, if you think about it, it is the same as before, because an equality between vectors is kind of like an equality between matrices. It just happens entry by entry. So this saying this is the same as saying this. Is that okay? So far, so good. But then the useful step is that if you remember, we did this already a couple of times. Like when you had like a vector that looks like this, like some weird combination of x's and y's, there was a matrix you could extract out of this expression, right? Like secretly, there's like a matrix hidden in here, right? I don't know if anyone remembers like what the matrix should be. What was the matrix that you could put in this case for this vector? Right. If you just read the coefficients of the that if you read the coefficients that appear in x and y, right, which are 1, -1, 3, 1. If you do that times the vector xy, right, you get back this vector. Is that making sense? So that's why at the beginning of the course last week, I spent some time like asking to find the matrix which would give you a specific vector. That's in part it was to do this sort of thing. So you can find the matrix from just reading out the coefficients, multiplying every variable. Is that okay? Well, that's going to be the solution. Yes. Are you correct? Yeah, that's going to be the solution. But right now, I'm just rewriting the equations themselves in terms of matrices. But yeah, like that's going to be the solution of this system. But so I'm just saying that this particular vector, which it looks a little bit more complicated, is really like the product of a matrix with like this vector, which looks a little bit more simple because this vector is just x and y. Is that making, which is kind of like the standard vector, you know, on the xy plane, it's just xy. So I'm saying that this, like the original equation, can be thought of, like the original system of equations can be thought of as the matrix A times this vector gives you the vector -1, 9. Is that making sense? So what this means, if you like the diagrams, for matrices is that you have like the vector xy, you put it through the matrix, right? Like think of the matrix as a machine. And we're trying to find, and we want this, that after you run this vector through the machine, you want the output to come out, right? You want the output to be the vector -9, 1. So in this problem, what's happening, right? What's happening in this problem is that I'm kind of saying, like, I know what the output is, right? I want the output to be -1, 9. Tell me what what values of x and y should you feed into the machine to get -1 and 9. So here in this problem, kind of the output is known, and you're trying to find the input that will produce that output. Is that making sense? So here, oops. The output is known, and we're trying to find the input that will give us that output. Is that making sense so far, so good? Um, Let me put another one. Let me do another one just to see if this is making sense. So let me put another system of equations. Here's another example. Okay. So you have this system of equations. Now I'm doing 3 variables, 3 unknowns. Right. So what I'm saying is that if you wanted to rewrite this system of equations in terms of matrices, you turn the first this one, these 3 numbers into a vector. So it's 1, 3, 0. And these 3 equations into the entries of a vector. So you get x minus y plus z to x plus z, and then minus x plus 3y plus 5z. Is that okay so far, so good? And then what's happening here? So what I'm saying is that in this case, we can still extract a matrix out of these equations. What's the matrix that you would get in this case? What are the entries? Good. Yes. Perfect. 1 minus 1, 1. And how about the second row?
2, 0, 1.
Yes, you have to just be careful here about the one in the middle being a 0 because there's no y present, correct? And then you have minus 1, 3, 5, right? So, and that's times what? Times a vector x, y, z, right? So you can check if you call this like the matrix A, right? If you do A times this vector, you literally get back this original vector from before. So you see, like secretly in the system of equations, like again, now, if you want to think about the machine version of the matrix, that you have the matrix A as a machine, right? I'm not going to write it again because it's too tedious. So you have the matrix A as a machine, you start, I don't know what this input is, but whatever this input is, I want it to spit out the vector 1, 3, 0, right? So it's like in a factory where you know what, it's like in a factory where you knew like the output, like the end result of the product you're trying to sell, right? And you're just asking what's the raw material you need to start with to get that end result. So just give me 1 second. Okay, and so let's do one more before I tell you. So I tell you what this looks like. So in general, here's another example. So let's say, which is a little bit nicer because you'll see. Okay, you'll see why it's more interesting maybe from the ones that we have been doing. Okay, so this one is just a slightly more interesting one because there are 4 variables, x, y, z, w, but only 2 equations. So it's not like equal number of variables as equations. So that's the only reason why this is a bit better, I guess. So again, the first part of rewriting this is just relatively straightforward, just entry by entry, like, the equations become the entries of the vectors. And now you do the same. It doesn't matter that there are like fewer equations than variables. You can extract still a matrix out of this. It's just now that the variables are x, y, z, w, right? So what are the coefficients here? They are, again, the entries are the coefficients of multiplying each variable. So it's 1, 1, minus 1, 2, and then 3, minus 1, 1, 0. Is that making sense? And notice that this is, so if I call this like this matrix, this is a matrix which is 2 by 4, right? And this vector is 4 by 1. And if you remember like how the matrix multiplication works, like this like in the middle go away. And so you should end up with something that's 2 by 1. So that's fine. This is okay. So that's also why we talked about matrix multiplication before, so that this would make a little bit more sense. Like what's going on here. But it is the same. Like now, if you want, you have this machine interpretation where you're running it through the machine A, and you're asking when do we get the output 5, 0. Is that okay? So the machines are allowed to kind of the machines can't change the size of the vector you start with. So here you started with something of size 4, and you can turn it into something of size 2. It's kind of like squishing out the vector, right? So that's okay. So far so good. Any questions up to this point?
So professor, you mean like the x, y, z, w can transpose to the 5, 0?
I mean, well, it's not the XYZ per se. It's like it will. It's not that the XYZ W become 5. It's just that this can be like the machine. What it's doing is taking it's taking this particular combination of X, Y, Z, and W, right? And I'm asking, when can I make this combination of X, Y, Z, and W equal to the number 5, right? Or where can I make this combination of X, Y, Z equal to the number 0? But so you see, like it's just taking like it's kind of taking many variables at times and combining them. Like it's kind of like a potion, right? Like chemistry, whatever. You have like different molecules and you're combining them to get like a new molecule or whatever. Like so it's like you started with basic elements and you're turning to, combine them in some mixture to get a new element. So it's kind of what's happening here. It's just like the way it's taking this particular machine, right? Because not all of them would do the same. The way in which this is kind of combining the variables is like through these coefficients, right? But there would be others that could combine them through other coefficients and things of that sort. Is that making sense?
Yes. Thank you.
No, sure. But my point is that in every system of linear equations that you see, you will always have a matrix. You have a vector of unknowns, right? Because if you look at this vector, it is a vector of unknowns or variables you don't know the values of. And that's being set equal to some vector that in general you know. Okay, so let me try to summarize that idea. And that's essentially what makes a system of equations a linear system of equations, that you can write it in this matrix form. So just to summarize, summarizing any system of equations, any linear system of equations can be written as A times X equals B. I mean, I'm just using the notation that's common in all the textbooks. So let me explain what that means. A is just like a matrix here, right? So A here is like the matrix that can be formed from the coefficients multiplying each variable, right? That is formed from the coefficients each variable. X is what you would notice that this X is not the variable X. It has like an arrow on top. So you want to think about it as a vector. So X is like it's like a vector of variables or unknowns. So like X could be, for example, XY, or X could be like XYZ, right? Or X could be XYZW. Or like, for example, if you start getting tired, you can just call it like X1, X2, X3, X4, X5. If you know, because maybe you get tired of trying to look for letters in the alphabet for each variable. So once you start having a bunch of variables, it's not useful to keep using different letters. It's just better to put like a number under X, underneath X, like a subscript. So etc. So X, when you have X in this with the arrow on top, you're referring to it as a vector of unknowns, and B, this vector B is the output, and it's just some vector which in general is given to you, right? So it's a vector which is given to you. Okay, so if you notice all the, so just to go back, sorry for a second. This is B in this example. This is B in this example. This is B in this example. So in every example, the right hand side of the equations is just what makes up the vector B. Okay, so the entries are the right hand. So the entries are the constants that appear at the end of each equation, right? Are the entries are the constants or the numbers which appear on the right hand side of the equations. Is that making sense? So, okay, now I can start telling you how to solve the systems of equations. Okay, so now the next question is, how do you solve the systems of equations? Okay, and again, like in a sense, like you kind of know how to do this, but you kind of know how to do this in a very case by case basis. So sometimes, like what people will do is that you solve for one of the variables, and then you plug it in into the other one, and then you keep trying to do some method of substitution or some other sort of cancellation, and that's fine. It's just that we want something that you kind of, no matter what the problem, you always do the same thing. So we're trying to find like what you would call like an algorithm, right? In the sense of like computer science, where you literally, this is what literally you would program into a computer to do. Where it is unambiguous, every step is kind of works in the same way, and there's kind of almost no choice on what you are supposed to do. So we're just trying to find like a way to minimize the options that you have so that you always do the same. So we're trying to find an algorithm. Yeah, this is what is called the Gaussian elimination. If you or the Gauss-Jordan method, like if you want the name, yes, Gauss-Jordan method. Um, I mean, I'm not 100% sure. Like many times, like who gets the name? It's not. Sometimes, yeah, the names are not very well assigned to whoever came up with it. I could imagine like many people came up with this idea. So I don't know if Gauss and Jordan were the first ones, but many things they just get their names because they made a lot of contributions. So, but yeah, like this is what, if you check textbooks, it would be called like Gaussian elimination, or yeah, Gauss-Jordan method or something of that sort. Row reduction of the matrix. Also you could call this like a row reduction of the matrix, and you'll see why in a second. So it goes under many different names. Yeah. So here's the thing, like the issue is that you have to decide what are the operations that you're allowed to do. So it's just like the point of this method is just kind of to choose like a very simple set of operations. So you'll see that the idea is that you choose uh, a list of operations that will not affect the solutions of the system, will not affect the solutions to the system of equations. Okay. So only when okay, so if it's just that terminology may not make a lot of sense to many at the moment, but like I'll put it this way: uh if it's just solving the system of equations, you will just stop wherever it's clear that it's easy to solve. When it's finding the inverse of a matrix, which I'll tell you maybe tomorrow, you kind of have to reduce it to the row reduced echelon form, because like you need to get to the identity. So, but except for finding the inverse of the matrix, like you know, yeah, you don't have to, like, you stop wherever you feel like stopping, basically. Like that's okay. Like in fact, like in many cases, like yeah, you can just like leave it upper triangular, and that from there you can see the solutions. But maybe we should get into those details later on. But yeah, typically I won't get like into too many distinctions about that stuff, because I find it like too much terminology. I'm not a big fan of a lot of terminology. So yeah. So, but yeah, I won't. As long as you know how to produce a system, like the solutions to the system of equations, I'm not too concerned on how much you reduce the system. That's how I'll put it. So, because yeah, like at the end of the day, this is to help you solve the equations, right? So not to make anyone's life harder. So option one, like operation one, is very simple. It's just a change the order in which the equations appear. It looks very silly actually, and it's the most simple silly of all the equations. So it's just change the order in which the equations appear. Okay, so but it's useful to kind of just see what that means. So, and I'll start explaining you like the notation that we'll use for this. So like, here's like an example. If you have x minus 1 equals -1 and 3x plus y equals 9, right? If I had give you those two equations, you can call them 1 and 2. And like this operation, what it's referring to is just to change where, the places of 1 and 2. So you're going to exchange equation 1 with equation 2. And so that literally means go make 2 appear first, right? Because now equation 2 goes to the slot of 1. And make 1 appear second, right? So it's really just like a reordering of the equation. Which again, it looks like a very silly thing to do, but you'll see why this is kind of convenient sometimes. The point is of doing that is that, like, I mean, you're just writing the equations in a different order that cannot possibly affect the solutions of the equations, right? It's kind of like a convention which one you write first, right? So this kind of has to preserve the order of the this has to preserve the solutions of the equation. There's no way this would affect it. Okay. Now, if what's more interesting is to look at what happened here if you write it in terms of the matrices, right? So how is the first system written as a matrix? It would have been, remember, it's just looking at the coefficients of the that are multiplying the equations, right? So you would write the first one, you would write as 1 minus 1, 3, 1 equals -1, 9, right? And how would you write the second one in terms of matrices? You would write it as 3, 1, 1, -1, x, y equals 9, 1. Is that everyone okay with that? So everyone's, is that making sense? So in terms of the matrices, what's the effect of changing the order of equation 1 with equation 2? How is that reflected in terms of the matrices? Oh, because that is because it was a typo. To answer your question, good, thanks. Good. Yeah, no, I agree. Did I copy the other stuff correctly? Yes. So what's the right? So what's the relation between these two matrices? Like, what's the relation between, in terms of the matrices? What happened when I changed the equations, like the order? What happened with the matrices in this case, or the vectors as well? So you see, like the first row, which was here, became the second row, right? And the second row became the first row, right? And the first entry became the second entry, and the second entry became the first entry. Is that making sense? So in terms of the matrices, what happened is that you literally swap the positions of the rows, right? If you so in terms of the matrices, what you did was change send row 1 to row 2 and row 2 to row 1. Is that okay? Are there any questions about this so far? But you see, the important thing is that kind of XY really did not change. The thing that was changing in our presentation of in terms of a matrix is like the numbers, like the entries, the coefficients, not like the variables. It's just all like the convention for writing the variables is always X, Y, X, Y. So that's not changing. So what's more usually for these systems of equations, since you don't want to kind of mess this up, you know, you kind of implicitly don't write X and Y. So just as a notation, which is what you will see, since XY always appears as X in that order. So since XY always appear in that order, you kind of remove it from the equation and you just put like a vertical line instead. So you remove them from the equation and put a vertical line in its place. So what I'm trying to say is that this, like the way in which this is written, instead of continue writing X, Y, X, Y, you will just write 1, -1, 3, 1, and this gets the XY gets replaced with a vertical line, and then you just write -1, 9. Okay. And similarly here, instead of like writing it where X and Y is written explicitly, you just write the you write like a vertical line in its place, and then you just write 9, -1. So in that way, the operation that we just did, it just literally looks like changing the rows of all of these. Like this first row goes to the second row, and the second row goes to the first row. So it's kind of like just like a more simplified notation, so that you don't have to keep writing X, Y, X, Y, X, Y every single time. Is that making sense? I'm about to do more examples with this notation so that you see what's going on. But I'm just trying to say that it kind of like the vertical line is a placeholder for X and Y. So it's not that you have eliminated them, it's just that you kind of keep them, they're kind of behind the wall. You know, they're there, but like they're being hidden from you because they're just like taking up space. So the first operation, like, again, the first operation is just changing the rows. Sorry, yeah, changing the rows or changing the order of the equations. Okay. So that was operation 1. Operation 2, okay, let's go to operation 2. Operation 2 is to multiply an equation by a number which is non-zero, multiplying or dividing an equation by a number which is non-zero. So let me write that down. By a non-zero number. So just to go back to the original, I'll keep doing all this first in the first equations and the original equations that I have been writing. So x minus 1, y equals negative 1, and 3x plus y equals 9. Okay. So what I'm doing here is the second operation is to, like, for example, you see it can be convenient. You might say, well, I would prefer to see, I don't like the fact that this equation starts with a 3. And you'll see why, maybe you may see why in a couple of minutes. Maybe you could say, I don't like the fact that this equation starts with a 3. So what you can do is like multiply both sides of the equation by 1/3 or divide both sides of the equation by 3. So let me write that down here. So what you could do here is so we're going to multiply equation 2 by 1/3. So what happens if you do that? You get x minus y equals -1. That doesn't affect the first equation at all. And then when you multiply the second equation by 1/3, this one becomes an x, right? The other one becomes y over 3. And the other one, the last number becomes a 3. Is that making sense? But obviously, this equation is literally the same as this equation, right? Because, if you want to go from here to here, you just reverse the operation, and you just multiply by 3, right? So it is like, this cannot affect the solutions again, because you can always undo the effect by, by just multiplying by the reciprocal of what you did before. Is that okay? Is that making sense? But let's look at how this looks from the matrix perspective. So if you write the first one in terms of a matrix, you would write 1, -1, 3, 1, -1, 9, right? And which again, let me. Sorry, I'm already jumping my step, skipping a step. So you could write it as xy equals -1, 9, which I'm saying that if you want to save yourself some space, you can write in this way. And if you take the second if you take the second version of the system, right? This is 1, -1, 1, 1/3 times xy equals -1, 3. Which, if you write in the short simplified version of the equation, I mean, with this vertical line, is 1, 1/3, -1, 3. Okay, so you see, regardless of how you choose to rewrite it, multiplying the second equation by 1/3 is literally the same as multiplying every single entry of the second row. Equation 2 is corresponds to the second row. So it's literally multiplying every single entry of the second row by 1/3. Okay, so it's easier to see that without having this annoying xy everywhere. So what I'm trying to say is that this operation becomes equivalent to multiplying every entry of the second row by 1/3. So in terms of matrices, what we did is multiply every entry on the second row by 1/3. Is that making sense? Everyone's okay so far, so good? Is that okay? Questions up to this point? Okay, so far I have been I started with the most silly operations. Like the first one was to just swap rows, right? Or swap the order of the equations, change the order of the equations in which they appear. The second operation was to multiply a given equation by a particular number, or you can think about it as multiplying or dividing by a non-zero number. And then there's one that's left, and that's kind of like the most interesting equation. Kind of, it's like a replacement for the method of substitution. Okay, so that's where like there is a little bit of you're doing something to the system, which is a more like definitely not as silly as what we have been doing. So that does require, that's a little one, that's the one that's a bit more tricky. So let's just to make sure your minds are fresh. Let's take like a quick 4-minute break. And when we come back, I'll tell you what it is, because it does better to just have a moment of time to not see them right one after the other. So let's meet in 5 minutes, and when we come back, I'll tell you the last, and that's the last operation. There's only 3 operations, but this one is a little bit more complicated. So I'll tell you about that one in 5 minutes. Okay, so let me tell you the most complicated operation of the 3. And this is the one about combining equations. Okay, so this is what it calls like, it's what it's called like a linear combination of the equations. So this is the last operation. So it's called a linear combination. So yeah, this one does require a little bit more of explaining on what's going on. Even the notation can be a bit tricky. So let me go back to our favorite system of equations, which is this one. So let's call these equations 1 and equation 2, right? Well, let me put this like this. So what happens, and you'll see that especially tomorrow, because tomorrow we'll spend a lot more time like solving systems of equations. But what happens here is that the idea to solve systems of equations is that kind of you want to start making a bunch of zeros or start eliminating some of the variables. So for example, if you look at this system corresponds to this matrix, right? That was the matrix that corresponds to it. And here we don't even see a single zero. So there's not a single zero on this matrix. And we would like to start putting zeros here, because the more zeros there are, the fewer variables appear. That's kind of the philosophy. And so the easiest way, you know, you kind of want to put zeros like kind of alphabetically or like in an some sort of ordered way. So the first thing that you could do is to try to put like a 0 here. Okay, so by that I just mean that I want to eliminate this 3x. I don't want to see it anymore. I want to see 0x instead. Okay, so how can you do that? Well, I'm about to erase this in a second. But if the equation had just been minus x, right? If the equation had just been minus x, how would you get a 0 here? Well, you could just have added the equations, right? If you add the equations, you get this goes away. But here we don't have minus x, we just have 3x. So we have to do kind of something similar, but with just a minor modification of that idea. So to get a 0 here, what you can do is like multiply this equation by -3 first. And then once after you multiply by -3, you add it to the second equation. So what I'm saying is that we're going to do that I just wrote. So I'm going to do -3 times equation 1. And I'm going to add it to equation 2. Okay. And the point is that you kind of want to preserve like the number of equations. So since this system had 2 equations, after doing this, I want 2 equations as well. So you kind of have to decide which is the equation that you are going to keep. So what we're going to do is just kind of use this as a replacement for equation 2. So what this arrow is going to mean, again, I said this was a little bit more tricky, but what this means is I'm going to do multiply equation 1 by -3, add it to equation 2, and that's going to be the substitute for equation 2. Okay, so let me show you how this looks like, because you might be confused right now. Okay, so now what I'm saying is that I'm going to multiply equation 1 by -3. And I'm going to add it to equation 2. And let's see, I'm going to multiply equation, and I'm do that on both sides. So multiply equation 1 by -3, you get this, and you add it to equation 2. Okay, let me see if I can write all of this in a more succinct notation. So, this gives you so I'm keeping equation 1 as it is. Okay. The only one that's going to be replaced with is equation 2, which is what this notation is indicating. Okay. Is that making sense? What I wrote? So again, it's kind of it's kind of basically the same as adding the equations. It's just that you, before adding the equations, you are allowed to multiply one of the equations by a number. That's basically it. So if there were no 3 minus 3 here, it's just like saying I'm just going to add equation 1 with equation 2, which is something you may have done in the past, right? When like you were solving systems of equations in high school. So we're doing exactly the same. It's just that before doing that, we are just now allowed to multiply one of the equations by a number. So it's like a slightly more general way of adding equations. Okay, and what's the advantage of doing that? What happens with this system of equations? What does that become? So you see, like the thing is that this -3x cancels this 3x. That's kind of why we chose it that way. So you get 0x. And what do you get for y? You get -3 with -1, that gives you 3y, and there's a y here, so you get 4 plus 4y, right? And that gives you, and then what do you get on the right-hand side? You get -3 with -1 is 3, plus 9, it gives you 12, right? Is that making sense? So that's the new system, how it looks like. Is that okay? So just to compare the two, let's do a before and after. So before you had this, oops, I should have done, I regret doing this that way. Let me make this a bit smaller. Okay. So this is what you had before. And now this is what you have after doing this operation. So how does this look in terms of the matrices? Right. Well, this one looked like 1, -1, 3, 1 times xy equals -1, 9. But as I have been saying, like xy is kind of annoying, so you can just put like a vertical line instead. Okay, so the before looks like that, and the after version looks like what? It looks like 1, -1, 0, 4, -1, 12. Sorry, I wanted to write it first with x or y. But after, like with the vertical bar notation, it just looks like -1. It looks like 1, -1, 0, 4, -1, 12. Okay. So in terms of the matrices, it's a lot easier to see what's happening. In terms of the matrices, what you literally did was, so in terms of matrices, what you did was multiply the coefficients of the first row by -3 and add them to the coefficients of the second row. So in terms of matrices, we multiplied each coefficient of the first row by -3 and added that to the, sorry, by -3 and added that to the second row. Which the way in which this is typically written out is like -3 row 1 plus row 2. Oops, I don't have enough space here. The way you would write this is as an operation is -3 row 1 plus row 2 replaces row 2. That's kind of how you would write that operation. Okay. Is that making sense? Yeah, well, yes, to make a 0 in one of the matrix coefficients. Correct, yes. Yeah. It's kind of like the only way to get zeros, because if you look at it, how can you get zeros from the operations, right? So the first operation only swaps the rows or the equations, right? So that cannot generate zeros, right? There's no way to get zeros from operation 1, right? And then in operation 2, you're multiplying or dividing by a non-zero number. So that also cannot give you a 0, right? So operation 3 is the only one to get zeros in the matrix. Is that making sense? Let me add it as a remark. This operation is the only operation that we have to produce zeros. This is only operation we have to get zeros in the matrix. And just as a more like okay. This is more like a conceptual thing, but it's kind of useful to know it. Let me write it here again. So like I showed you, like again, I did this to put a 0 here, right? To get a 0. In the previous two cases, with the other two operations, it was clear that you could always undo the operation, right? Because if your operation is changing row one, equation one with equation two, then you just change them back if you kind of regret what you did. And if in the second operation, if what you did was multiply by 3, and you regret that, you can just divide by divide by 3, right? So in the first two operations, it's always clear that you can always, if you have regrets, you can always go back, right? So my question is like, imagine that, like you are here, right? And you regret what you did, like you feel bad, or you want to take it back. Is there a way, right? Would there be a way in this, from starting from this one to get back to the original one? How could you get from like, so I'm going in reverse, right? I'm asking, is it possible to go in reverse? What operation could you do here with from here to go backwards? What do you think? So how can I go from the purple one to the blue one? What would you use? So you kind of regretted what you did. Now you want to undo that effect of the operation. What sort of thing could you try? So that means that I want to see a 3 here, right? That's kind of what it means to take it back, right? So how could you put a 3 here? That's like my question. How can, if I have a 0 here, how can I put a 3? What could you do? Yeah, exactly. Good. So you could do 3 row 1 plus row 2 into row 2. So check that this works, right? If you do 3 row 1, now this becomes 3 with this 0, it gives you 3. This one becomes negative 3 with this 4, gives you 1. This one becomes minus 3 with this 12, gives you 9. Okay, so, and that's actually more or less what happens all the time. So if you do like, for example, a row, I mean, it doesn't matter which one, which rows you're doing it, but just to make it more concrete, if you're doing a times row 1 plus row 2 into row 2, you can undo that, reverse that with minus a row 1 plus row 2 into row 2. So it's just like taking the same coefficient, but with the opposite sign. So here a was like negative 3, so minus a is minus 3, which is 3. So the only point for bringing this up is that this operation, the idea is that every operation that we're doing on the system of equations can be undone, and that is kind of what guarantees that we're not messing things up in the sense of like losing solutions or things like that. Because if you can always take back your steps, then that's not affecting really the solutions to the system of equations. So operation 3 is also what you would call reversible. So operation 3 is reversible as well. So we're never, so none of these 3 operations will affect so all the 3 operations will preserve the solutions of the system. Will not create like fake solutions or anything like that. So all the, like, so the 3 operations we just studied, will preserve the solutions to the system of equations. Okay. So, I mean, this is more like a theoretical remark, but it's just for people to, like, just to make it clear that we are never doing anything that does like an irreversible damage to the system. Like you can always revert. It's kind of like the unsend button, like when you just send an email, right? That you can. Well, I guess that option is only for a couple of seconds, right? I don't remember for how long you have it available, but it's kind of like an indefinite unsend option, right? Like you can always unsend the undo the operation that you were working with here. Is that making sense? Okay. Okay, and maybe now I can show you finally what's the point of doing all of this. So the goal, and I'll show you how to do it in this particular system we have been working on. So the goal, the goal for solving systems of equations is to apply these operations on the system so that you get as close as you can to the identity matrix. So let me explain what the goal is. Okay, so the goal. So you have a system of equations. Which we write as ax equals b. Remember, that's another way to write the systems of equations now with the help of matrices. Or if you prefer the vertical line notation, you can write it as a b. That's like, again, these two things, like if you don't want to see like the variables explicitly, you can like put the vertical line, and that's what we'll do because it just saves you a little bit of time. Okay. So the goal, the key you'll see to solve these systems of equations is that you apply operations 1, 2, and 3 to turn A as much as possible into the identity matrix. And I'll clarify what that means, like between today and tomorrow. But the idea is to use the operations 1, 2, and 3. 1, 2, and 3 to transform the matrix A as much into the identity matrix as much as possible. Okay. Okay, so let me show you that at least first with this example, we have been doing like multiple occasions. So let me show you how this idea can be applied to the example we have been working with. So let's solve let's solve this one using that principle. So let's take x minus y equals -1, 3x plus y equals 9. Okay, and let's try to solve this. So again, the first thing you can do is like rewrite it in matrix notation. So you can write it as 1 minus 1, 3, 1 times xy equals negative 1, 9. But again, at this point, like, you know, all of this junk can be changed into the vertical line. So it is just fast. It's more, it's just more convenient to put like the vertical line here because that way you only see the coefficient of the system, like the numbers that appear in the system. The variables x and y are kind of always the same. So you do that. And again, this is kind of like our matrix A. This is our vector B. So the goal is to turn this as much as possible into the identity matrix. Okay. And you'll see why in a second, like once we get to the identity matrix, why that's convenient. But what does it mean? What was the identity matrix? The identity matrix was 1, 0, 0, 1. Okay. So again, our ideal is to, like, the identity matrix is 1, 0, 0, 1. So what that means is that you start with a 1. This is good because this already has a 1 here. Okay. And then you kind of move like in some sort of like zigzag. So you kind of have to do like a motion of this form. Again, think about this as like an algorithm, like something you'll feed into the computer. So the computer would check first if there's like a 1 here. If that's good to go, then it would just go through the other numbers, like in this kind of zigzag version. So from this 1, the computer will move down, and then now the computer says, okay, there's an issue because you don't have a 0 here, you have a 3, right? But we saw that there is a way to put a 0 there, right? What was the operation? We could do minus 3 row 1 plus row 2 into row 2, right? So that's what we could get to, what we could do to put a 0. And we had computed this before, right? You get a 0 here with minus 3, and then this gave you a 4, and then this one gave you a 12. Is that making sense? So, and then again, our goal is to make this as much as possible into the identity. So now you could, like, what you would like to do is to put a 0 here, right? I mean, you want to put like a 0 here, and you would also like to put a 1 here. Like those are the remain, like now you have to deal with the column. So yeah, maybe in the diagram, I mean, you can do a zigzag like this, but you can also just like it will be maybe easier if we go this way. So what, it kind of both don't make much of a difference now. I'll give you more of the rules more precisely next time. But what you could do, like for example, is to put a 1 here. So how can you put a 1? What could you put? How could you make a 1 in this entry? Yeah, exactly. You can do a 1/4 or a 1/4 of second equation. Perfect. How can we write that? It's 1/4 of second equation. Okay, and that I mean, that's kind of unambiguous. Like it's what you're trying to do here. So you do 1 minus 1 minus 1. Nothing happened to the first row or the first equation, and then the second one becomes like 0, 1, and 3. Okay. And we're almost there, because now the only thing that's left is to put a 0 here. Again, there's only one way we have to put zeros, which is operation 3. Okay, but for now what you need to put a 0 here is to add this equation to this equation, right? So you can do row 2 plus row 1. If you add them together, these two numbers will cancel and give you a 0, but now the replacement is going to be in row 1, right? Because now row 2, I'm happy with how it looks. Is that okay? So let me see. So now nothing is happening with the second row, and let me just write all the details for this operation. So we're doing 2, 1, 3. Right, so I'm taking the numbers of the second row, which are 0, 1, 3, 0, 1, 3, and I'm adding them to the numbers of the first row, 1, -1, -1. In practice, you usually wouldn't do this step, but I'm just showing everything right now so that you can see it. And so you get what? You get 0, 1, 3 at the bottom, and then you get 1, 0, 2. Is that making sense? Oh, but we won because we got to the identity, right? And so what's the here in this case, we actually got the identity. You'll see tomorrow that you cannot always get there. We kind of have to get as close as possible to the identity, but you won't always succeed. But in this case, we could. And what's the price that we get for getting to the identity? Well, that literally, if now that you got to the identity, it's kind of useful to, you know, like really remove the vertical line. So that means like xy equals to 3. That's actually what the system now means. But remember, the identity times anything is just a vector. So you just get xy equals to 3. So you get x equals 2 and y equals 3. Right? So that's yeah, exactly. That's the point, because at every step you can always undo the operation, right? If you remember. So any operation that any of these 3 basic operations can always be reversed. So you can always get back to the original equations if you change your mind. So that means that if you put x equals 2 and y equals 3 and you plug it into the original system, you will find that this is satisfied. Yeah. So these solve the origin. So these 2 values solve the original system. Is that making sense? Which you can check literally here by just plugging in, right? If you put 2 and 3, you get 2 minus 3, which is -1. And here you get 6, and 6 plus 3 equals 9, right? Is that okay? And every single system of linear equations is literally the same. It's just applying these operations over and over. Operation 1, operation 2, operation 3. As much as you can to make as many zeros as you can, to put as many zeros and ones as you can in the matrix in order to get to the identity. That's basically the idea. So that's what we will do tomorrow. Tomorrow we'll do a bunch of examples, but you'll see after you do a couple, kind of, it's always the same. There's no, like, it's really the same process every single time. Kind of you reduce like as much. So this is kind of meant to reduce like the freedom that you had before, because before what you could have done like to solve the system was like, well, you maybe solve for one of the variables, then you do like a substitution, like you have different choices, right? Here we're trying to reduce the choices as much as we can. So it's like a more organized way of solving equations, which maybe you didn't have before, because like, yeah, you could have solved this before from high school, algebra, pre-calculus. It's not too difficult to solve. It's just not, when you would do that, like there were many options you could use, and we are trying here to remove options so that it's always the same, okay? Maybe, yeah, let's see if I can show you this. That's good. It's useful before we move on to the quiz. It's also useful to check Wolfram Alpha if you have done it, used it before. Let's see. That's a good thing about linear algebra. It's literally the basis of most computer programs. So there are many tools to solve linear algebra equations, and especially for something as easy as what we have to deal with. So well, you can write something like this in Wolfram Alpha, and let's see if what interpretation. Okay, it's giving you that interpretation. So if you want to do it, in the matrix way, let's see if you can find it in the matrix equation. Yeah. Oh, okay. You would have to say reduce, row reduce. So here, like if you wanted to do it, put in Wolfram Alpha in the matrix version, you would put like the coefficients that we found. So the coefficients we had were 1, -1, -1, 3, 1, 9. So I mean, I have to include like you'll see the last column there's no way to put the vertical line on Wolfram. So the last column refers to the coefficients of the vector B. So you see, if you look at the first 4, those are like the coefficients of the matrix, and the last 2 are the coefficients of the vector B, and it gets to the identity followed by 2, 3. So that's actually what's going on. Yeah, you can turn you can turn a row into yeah, and once we have like 4 rows, you can do like row 2 with row 3, or row 4 with row 1. Like, yeah, you can like combine the rows essentially. Yes, that's the idea. So yeah, so this method is called row reduction method. So yeah, but the good thing that I like about linear algebra is that it's always good to the fact that you can always check it here, because like it's really only that, like solving systems of equations. So it's just that if you enter it on Wolfram Alpha, you just have to make sure to enter also include in what you write on Wolfram Alpha the coefficients for the vector B. Okay, but as I said, tomorrow we'll do a bunch more examples so that this starts making more sense. But it's really just that, just applying operations 1, 2, and 3 in a sort of systematic way. Okay, that making sense? So yeah, and like here you can play, you can play with other, like if you want to play with your own systems of equations, you can just change the coefficients here and see what you get. So like I'll give you some examples to work on. Okay, so I think now this is a good place to stop for today. So yeah, I'll make the quiz available. Oh, the only thing before you leave, did I make it here? Okay, no, it's already here. Yeah, so you should, yeah, I'll post it now. You should have seen, you can now access it, and just remember to upload your solutions to the upload assignment. So besides that, yeah, I'll see you tomorrow. That sounds good.
Thank you,
Bye.
Professor. Have a nice day.
See you. You too. You too. Yeah. If you know how to find the inverse matrix, you can double check with that. Yeah. I'll tell you about how to do that probably tomorrow or Thursday, but yeah, you can do it now if you want.